Assalamualaikum warahmatullahi wabarakatuh. Hi everyone. So this is a recorded lecture for mechanical properties of materials that cover two learning objective. First one is to understand how to measure the stress and strain through the experiments, and the second one is to correlate the behavior of some engineering materials to the stress strain diagram. Okay. The strength of a material depends on its ability to sustain a load without undue deformations or failure. So how to characterize this property, the strength of the materials? So there are two types of tests that we commonly use. First one is tensions and compression test, which is tension and compression test. So the figure shows you samples and a sample for tensions and compression test, and the right part of the slide shows you the tensions and compression test machines. So the tension and compression test machine consists of a movable upper cross head, okay, the tension specimen at the center over here, and also a load cells at the bottoms. Okay, the samples for compressions and tension tests usually we call as a dog bone sample. Okay, so you have at the center part over here we call as a gauge length. So the gauge length is where we measure the deformations of the samples. Okay. So let's move to the next slide. Okay, so this figure shows you the stress strain diagrams of a metal. Okay, so so in this figure, okay, as you can see over here, there are elastic regions and also plastic regions. Elastic behavior of a materials occurs when the strain in the specimen are within the light orange region as shown in the figure. Okay, you can see over here on this area. Okay, so we call as elastic regions. Here, the curve is actually a straight line throughout most of these regions, so that the stress is proportional to the strain. And the material in this region is said to be a linear elastic, and the upper stress limit, okay, the upper stress limit to this linear relationship is called the proportional limit. Okay, so the proportional limit so this one, the proportional limit, which is the most the upper limit in the linear part of the graph. Okay, so if the stress slightly exceed the proportional limit, okay, if we can zoom it over here, okay, you can see if the stress value exceed the proportional limit, okay, the curve tend to bend and flatten out as shown in the figure over here. So in this area, okay, we can see the graph started to bend and flatten. So this continue until the stress reach the elastic limit. So you can see they started to curve and then it reached the elastic limit, and then upon reaching this point, okay, if the load is removed, the specimen will still return back to its original shape. So that means if you pull a sample and the stress value reach up to elastic limit, and then you remove the load, the sample will goes back to its original shape. Okay, so however, if it exceed the yield stress over here, okay, okay, if you reach the yield stress, the yield point over here, the sample, when you remove the strength, it will not, if you remove the stress, it will not move back to its original shapes. Okay, so you need to remind. So this area, in this area, in the elastic region, the material behave elastically, and if you remove the stress before it reach the yield stress, it will return back to its original shapes. Okay, so then we go to the second area, which is the yielding area. As you can see in this graph, shaded with brown color. Okay, a slight increase in stress above the elastic limit will result in breakdown of the material and cause it to deform permanently. Okay, so this behavior we call as a yielding, and it is indicated by the rectangular dark orange region in the curve. So the stress that causes yielding is called the yield stress. Okay, so as mentioned earlier, so the stress that cause yielding we call as the yield stress or yield point. It's yield point, and the deformation that occurs we call as a plastic deformation. So that means that starting from yield stress up to the fracture stress, plastic will sample will behave plastically, and it we call as a plastic deformations. So in this area, if you remove the strength, if you remove the stress, the sample will not return to its original shape, and it started to already experience, it was already started deform. Okay. Okay, so then we go to the next area. Okay, colored with the light green over here at the center over here. Okay, in this area, okay, the strain we call as the strain hardening. So when the yielding has ended, an increase in load can be supported by the specimen, resulting in a curve that rises continuously but become flatter until it reached a maximum stress. Okay, so it reached the maximum stress over here. You have an ultimate stress, and we can call it also as a maximum stress. And then if you notice, so up to the ultimate stress, as the specimen elongates, the cross-sectional area will decrease. So if you go more than the ultimate stress, you can see over here the stress started to decrease, and the sample started to experience a necking. So you can see in the figure above over here on the right side. Okay, on the left part is a sample that is the original shape. On the right, on the right side is a sample that has started to experience necking. Okay, so this part is where the sample will finally break down or fractured. Okay, so and also in this graph you can see there are two type of fracture stress: the true fracture stress and then the engineering fracture stress. Okay, this is true and this is an engineering fracture stress. So what is the difference between these two values? Okay, fracture stress is we calculated it based on the stress equal to force over area, isn't it? The area that we use over here is the area over here is the original area. Okay, that means area before it undergoes deformations. But for true stress, the area that we use to calculate the stress, practice stress, F over A, the area that we use it is the area that is after the sample deformed, the instantaneous area. Okay, so that's why the value that you will get for true stress will be higher than fracture stress. Okay, next.